To find the intervals on which a function is increasing or decreasing, we're going to use the first derivative test for relative extrema. First, we're going to find any domain restrictions, then any critical numbers, because that is where relative extrema happen. Then we're going to create an f prime number line where we will label the critical numbers and the domain restrictions, test the signs of f prime in each interval to figure out whether f is increasing or decreasing for those intervals. Number one is a cube root function. A cube root function doesn't actually have any restrictions to its domain. Its derivative may have a restriction depending on if you have a vertical tangent, but we'll check when we get to the derivative. So the domain for this function is all real numbers, negative infinity up to infinity. Let's derive and find critical numbers. For this one, I'm going to use the general power rule. Pop down, power down, u goes inside, and the derivative of u is multiplied out here, so 2x. I want to write it in radical form because it's a lot easier for me to see my restrictions that way. Time to find critical numbers. Critical numbers are where the derivative is equal to 0 or where the derivative is undefined as long as f is defined in that place. For f prime of x equal to 0, we are essentially making the numerator equal to 0, and if we do that, x equals 0 allows the numerator to be 0 but not the denominator, so x equals 0 is a critical number. To find where f prime of x may be undefined, we want to know where is the denominator equal to 0. And you may notice that under this root we can factor that difference of perfect squares, x plus 3 and x minus 3. And when you do that, you can see that positive 3 and negative 3 will both make this root 0, which will make our denominator 0. So our other critical numbers are negative 3 and positive 3. Time to make our f prime number line. Remember, on the f prime number line, we'll put domain restrictions, which we have none, and then our critical numbers, so negative 3, 0, and 3. To test out the signs of the intervals, I'm going to plug in values to the left and right of each of our critical numbers. To the left of negative 3, I'll plug in negative 4, and we're testing the sign of f prime, so we're plugging it into f prime. Negative 1 is between negative 3 and 0. 1 is between 0 and 3. Now remember, for testing the signs, we only care if it's positive or negative. We don't actually care about the number result. So when you plug in negative and we're plugging into the derivative, we have a negative on the top, and the denominator would be positive. For f prime of negative 1, when we plug in negative 1, negative on the top, and negative on the bottom, then we have f prime of 1, positive on the top, but negative on the bottom, and f prime of 4, positive over positive. From negative infinity to negative 3, f prime is negative, which means f is decreasing. From negative 3 to 0, f prime is positive, which means f is increasing on this interval. From 0 to 3, f prime is negative, which means f is decreasing on this interval. From 3 to infinity, f prime is positive, which means f is increasing on the interval 3 to infinity. We already determined that we're increasing from negative 3 to 0, 3 to infinity. We're decreasing on negative infinity to negative 3, 0 to 3. A relative maximum will only occur at a critical number where f prime goes from positive to negative, where f goes from increasing to decreasing. That is where we have a relative max. So at x equals 0, we're going to have a relative maximum. They told me to find all local extreme points, so not just the x values. A relative minimum will occur when f prime goes from negative to positive, which means f goes from decreasing to increasing, which indicates a relative minimum. And that's at the x values of negative 3 and positive 3. Let's plug those in to the f function to get our y values. Now for cubed root 81, we can actually simplify the radical. There is a perfect cube that goes into 81, and that would be 27. Which gives us our answer for increasing and decreasing intervals in all relative extrema. First, we check for any domain restrictions. Look at this denominator. Whatever makes it 0 is a domain restriction, and 0 makes that denominator equal to 0. So 0 is a vertical asymptote. That makes our domain negative infinity to 0, 0 to infinity. As a reminder, we need to label any domain restrictions on our f prime number line. I like to draw a little dotted line just to remind myself this is not a critical number, it cannot be a relative extrema, it is a vertical asymptote. Let's derive to find our critical numbers. I'm going to use the quotient rule. To find critical numbers, we're looking for where does the derivative equal 0 or where is it undefined. This is difference of perfect squares, but I don't need a factor because I'm only looking for the real and not the imaginary solutions. So x to the fourth equals 1. Then we'll fourth root both sides and get plus or minus 1. X is also equal to 0. But remember that 0 was a domain restriction. 0 was a vertical asymptote, so it cannot be a critical number. Therefore, our only critical numbers are at -1 and +1. Let's determine the signs of f prime on each interval by plugging in a number to the left and right of our critical numbers and domain restrictions. Remember, we're plugging these into f prime in order to test the signs of the derivative. Plugging into x to the fourth or x squared, both of those will make our result positive, so we just have to figure out if subtracting 1 will make the numerator negative or positive, because the denominator is always positive. The -2 to the fourth, that's going to be positive over positive. This is going to be negative over positive. When you plug in 1/2, you'll get negative on the top and positive in the denominator, and positive over positive, which is a resulting positive interval. F prime is positive on the intervals -∞ to -1 and 1 to infinity, and negative between -1 and 0 and 0 and 1. The graph of f will increase, then decrease, decrease, then increase. Now, when we put the decreasing interval, we have to remember that 0 is not a critical number, it is a domain restriction. So it cannot be inside of our interval. So we're actually decreasing from -1 to 0, union 0 to 1. You cannot write the interval all as 1, -1 to 1, because there's a domain restriction in there. Our relative max occurs when f prime goes from positive to negative, so at -1. Our relative min occurs when f prime goes from negative to positive, so at 1. We'll plug those in to find the y values. Remember, we're plugging these into the original function. And there is our complete answer. Our third example is a polynomial, so it is also continuous. We have no domain restrictions. Let's derive using the power rule. And to find critical numbers, again, we have another polynomial, so it is continuous. F prime of x will not be undefined, so we'll just make it equal to 0. I'm going to factor out the GCF of 3. X minus 1 equals 0, so x equals 1 is our critical number. And we only have one critical number to put on our f prime number line. Let's test signs to the left and right of 1. Both of these intervals are positive for f prime, meaning f is increasing on both of these intervals. In fact, f is increasing for -∞ to +∞. We do not need to break up our interval for this critical number because it's a critical number, not a domain restriction. We are increasing from -∞ to infinity. That means there are no relative extrema. Even though the derivative is equal to 0 at some point, it is not a relative max or min. This function is strictly monotonic. Strictly non-increasing or strictly non-decreasing functions are called monotonic. The reason why I use the words non-increasing rather than increasing or decreasing is because it could also stay constant, and that would be non-increasing but not decreasing. Example 3 illustrates two important points. Not every critical number produces a relative max or min, and even though the slope at x equals 1 is 0, the function is still always increasing. Strictly monotonic.